Okay, so basically, what we have always assumed, and this is what Newton would say, is that light is not affected by gravity, right? So I don't want to make that black actually this time, even though I'm talking about black hole. This is maybe the sun, or could be whatever, some sort of object. Now we know that if we had another object, it would be attracted to it because of gravity. And sometimes if it's flying just past it, maybe it gets captured in an orbit and goes around it like that. So it doesn't necessarily mean that it just crashes into it. It depends. Sometimes it might spiral away as well. Anyway, but light itself should not be affected, right? So if I had some rays of light, let's not make it a curve though, and we'll give it an arrow. So if I had some rays of light like this, then can I copy that? Right. They should just kind of like, well, not pass through it, like these ones in the middle are obviously going to come into contact with it like that. But they should just carry on going in a straight line. Now what Einstein showed is that they don't, in fact. So in actual fact that they do curve. So oops. So it kind of does this. So it doesn't bow out though. As it comes towards the object, it sort of gets attracted to it a little bit. Now we don't notice this effect too much, really, because the effect is minimal. Like it doesn't really get affected very much, but it does get affected. And Einstein, and the reason why we would have thought it doesn't get affected is because light doesn't have a mass. Okay, so there's no and so there isn't any force. The force of gravity is related to the masses of the objects, and light has no mass, so there should be no force. You can't apply a force of whatever onto something that doesn't have a mass. So it shouldn't be deflected, but it is deflected, and the reason why it's deflected is because gravity is not exactly a force. It might feel like a force, but it's much weirder than that. It's more the bending of something called space-time. Now that gets very complicated, so I won't go into it too much here. I won't go into it at all actually at the moment, but it's nonetheless, it means that light can in fact be affected by gravity. So, as I said, if the object has a larger mass, then it's going to be deflected even more. Okay. Now, if it's really large, like crazy gravity, let's get rid of the rest of these ones here. We could in fact get some really crazy curves around it, and in fact we could in theory have an orbit. So in other words, light would just keep going, would orbit the object if the object was massive enough. When I use the word massive there, I mean it's got a high mass. Okay, that's technically what the word massive means. It shouldn't really be to do with size, but so you can in theory it could just curve around if the force of gravity is large. Well, not the force, sorry, the effect of gravity is large enough, it will eventually curve around. Now that means that if I'm over here, I'm never going to actually see the object. So if I'm just looking at it over here, then no light is going to be reflected from the object, because any light that would be going that way would just, the effect of gravity on the light would curve back around again. It would never get away. So it's in the same way as if I threw a ball up in the air, it doesn't leave the planet Earth because I'm not strong enough to throw a ball up in the air. If I shot it up in the air with a really powerful cannon, probably still wouldn't leave the planet Earth. I actually need to go to make a rocket with rocket fuel and produce an extremely strong continual force, and to get anything into space. But if we trying to get something off the surface of a black hole, we don't even know what it is because we can't see it. But let's imagine it's a solid object. If we try to get something off the surface of that object inside a black hole, nothing could ever be strong enough to get anything off the surface, because not even light is moving fast enough to emit off the surface. So it just comes back down again in the same way as when I throw a ball up in the air, it comes back down again. So this is the reason why we can't see a black hole. Now, just in the same way, when you get near to planet Earth, or to any planet or star or moon, or anything in fact, the strength of gravity gets stronger and stronger and stronger. So it's not so much that we think, oh, this black hole's got a large gravity, and so therefore, all rays of light are going to just spiral in. All light is always going to go that. Of course not, because otherwise we won't be able to see anything. Like, all the light on our planet Earth will be shooting off into all the black holes in the universe. But we're obviously not. That's not really happening. It's only once you get close enough that the light goes into the black hole, and in this case, if it gets at this point here where it would orbit the black hole, this is when it's just at the point where it's not close enough that it's going to go into the black hole, but it's too close to be able to get away. And at that point, that exact point where it's just close enough that it's not going to escape or go into the black hole, we would call that the event horizon. Okay, the event horizon. Now, why it's called the event horizon is really weird. But it's got something to do with that if the light of an event, something occurring, cannot get away, then we can't even say that it's actually even happening. So there's this weird idea within relativity, as in what Einstein was talking about, that if we can't see something, then it's not actually really occurring. It's a bit weird. So, for example, if our sun exploded, it would take 8 minutes for the light from the sun to get to us. We wouldn't know the sun had exploded for 8 minutes. And because nothing travels faster than the speed of light, we wouldn't feel the effect of it in any way for 8 minutes. We wouldn't know about it. But more than that, relativity kind of claims it hasn't even happened for 8 minutes, even though in a way it has. It's very bizarre, but it's to do with to be honest, it's really complicated, so I don't want to go too much into that, but it's all to do with the idea that our version, we assume that time is the same for all people, but it's not actually the same for all people. Time is experienced differently from different people from different parts of the universe and so on. But so going to make it a little bit simple again, light can't escape if you get closer than this this point where we call the event horizon. Beyond it, if we go a little bit further away from that, it is possible for the light to escape, and therefore it's possible for other things to escape. If light can't escape, nothing can escape. Okay, So anything that, so you're never going to be able to see the black hole, because the only way we can see the black hole is for light to be reflected off it or light to be emitted from it. And so it would have to be close, it would have to be at the surface of the black hole and therefore beyond the event horizon, so we can't see it. Okay? But we can sort of see it because we can see the stuff around it. So there's this, and I think this is what you're talking about here, a disk of gas and dust that orbits a black hole so fast that it creates electromagnetic radiation. That's what we can see. That's not the black hole, that's just stuff that's orbiting the black hole. But obviously we could say that is like a signature of a black hole, so in a way that we are able to see where it is, we can say that we can see it. Anyway, it's a little bit like, imagine that you can't see an invisible man, but if you threw a load of flour over the invisible man, we can see him. But actually you can't really see him, can you? You can just see the flour on the invisible man. So we say that we can see the invisible man now. No, you could just see the flour on the surface of the invisible man. In the same way, we can't see a black hole technically, but we can see the stuff that's orbiting it. And so we sometimes say that we can see the black hole. Okay, I'm just going to stop the video there.